a chemical that on Earth is only produced by life. However, this discovery was unfortunately greatly exaggerated. First off, the dimethyl sulfide wasn't actually detected, only hints of it were. K218b's spectrum is consistent with and without the presence of DMS, and both scenarios fit the data. This is like TRAPPIST-1d. Yes, technically an airless rock and a Venus-like atmosphere both fit the TRAPPIST-1d data, but there's no actual reason to think the Venus scenario is accurate with all the other evidence suggesting it's airless. It's a similar situation with the K218b dimethyl sulfide. Sure, the data could be interpreted as it being there, but the simplest explanation is often the most likely, and a plant with zero dimethyl sulfide fits the data just fine. However, even assuming the dimethyl sulfide is there, there's actually no reason to think it's a sign of life either. Despite what you may have heard, DMS can absolutely be produced without the need for life. Also, if life was creating it, you'd expect other gases the type of life also produces to be there. Most notably, if the DMS was being produced by life, you'd also expect to see detectable amounts of ethane. There's no detectable ethane in K218b's atmosphere. This is all said in yet another paper in the description. So the dimethyl sulfide even existing in the first place is shaky at best, and the dimethyl sulfide being an actual sign of life is even less likely. The headline saying K218b has a 96% chance of supporting life or whatever is just made up, and I honestly have no idea where they got that number from. Anyways, let's now talk about what this planet might actually be like. K218b is 8.6 times the mass of Earth, 2.6 times larger in radius, and takes 32.9 days to orbit its red dwarf star. At face value, it seems like a much larger version of LHS-1140b. However, if you recall, the main reason we think LHS-1140b is an ocean planet rather than a mini-Neptune is because that planet lacks hydrogen. However, hydrogen has been detected on K218b, and its density is much lower than LHS-1140b. This provides strong evidence that K218b is not an ocean planet, but rather a small temperate ice giant. Unfortunately, it seems like nobody can actually agree on what is going on with K218b. Unlike every other planet so far, which only has one or two likely scenarios for its environment, people have speculated that K218b is everything from a paradise ocean planet to a dry ice giant to a super Venus lava world. So let's go over a few of those scenarios. First off, James Webb found evidence that methane and carbon dioxide in the atmosphere, though the existence of carbon dioxide is less certain. If this is true, then for these observations to make sense, K218b's atmosphere must make up about 6.2% of the planet's total mass. This suggests a composition similar to Uranus and Neptune, but doesn't confirm it. There are conflicting reports about the discovery of water clouds on K218b. Some people say they're there, others say they aren't. If they are there, they're probably icy, though liquid water is not off the table. Clouds made of chemicals other than water are unlikely, however there are small chances for other types of clouds to form. This is so hard to figure out because we don't know what type of haze exists in K218b's atmosphere. One paper suggests that based on the planet's hypothetical chemistry, a dense haze of sulfur gas may form. This haze layer would obscure the planet's atmosphere and be present both above and below the water cloud layer, making the characterization of K218b's atmosphere much more difficult than any other planet so far. Water vapor has also been detected, but only sometimes. Hubble found evidence of it, while James Webb observations showed that water vapor must make up less than 0.1% of the planet's atmosphere. However, this may be due to the presence of a stratosphere, as models suggest that a temperature inversion should occur on K218b, resulting in an upper stratosphere with no water that again would block the water signal and make atmospheric characterization difficult. So K218b's results have been largely inconclusive because, whether it be because of a sulfur haze layer, a dry stratosphere, or both, this planet seems to be fighting us the whole way. However, we can actually infer things about this planet based on what we don't see. For example, ammonia was not detected. Models suggest that a large global water ocean is capable of absorbing ammonia from the atmosphere, making it undetectable, and, if that's true, suggests that there is a clear boundary between ocean and atmosphere that could make K218b a proper ocean world. However, later work showed that an ocean of magma could produce the same results, and an ocean of magma is potentially likely due to the runaway greenhouse effect. However, a lava ocean can't explain the lack of observed concentrations of carbon oxides. But to make things worse, a water ocean can't explain the concentrations of methane, as it should absorb it all. Which leads to one paper suggesting that if K218b does have a water ocean, then the only way the methane can be explained is if life is producing it. But there's still one explanation left, suggested by that same paper, that explains the data without needing a water or lava ocean. K2-18b is just a normal mini-Neptune rich in gas with no solid surface. This can result in the amount of methane and potential amount of carbon dioxide, and most importantly, results in low amounts of water, ammonia, and carbon monoxide, which is exactly what we're seeing. So maybe the whole K2-18b situation is just being massively overcomplicated. Out of everything I've seen so far, it seems that a boring, dry, gas-rich mini-Neptune with no ocean and no life fits the data best. That's kind of unfortunate for K2-18b, but also remember that if you're looking for a planet that actually has a chance of having an ocean, look no further than LHS 1140b. But with that, the era of talking about endless mini-Neptunes ends. Jumping 301 light-years away from Earth, we reach Kepler 1649c. It's about 6% larger in radius than Earth, but with an unknown mass. It takes 19.5 days to orbit its star, which is, you guessed it, another red dwarf. It receives about 75% of the light Earth does, and is probably tidally locked. Everything I said at the beginning of this video about Proxima b and planets like that may or may not apply here. However, Kepler 1649c is very close to Kepler 1649b, the other confirmed planet in the system, roughly the same size and taking 8.6 days to orbit the star. This makes this system potentially a less extreme version of Gliese 667c. These planets, according to one paper, are close enough to one another to cause eccentricity oscillations, like what occurs for Gliese 667cc. However, because these planets are smaller, the eccentricity oscillations are far more mild, and models suggest that even though its orbit will be changing, the environment and surface temperature of Kepler 1649c should remain stable, and not enter a runaway greenhouse super-Venus state. Unfortunately, we know nothing about its atmosphere or environment beyond this. Very little research has been done into this planet. So I don't really know what it could be like, so I'm going to say it may have a chance of being habitable. It's very similar to Earth size, which is probably nice. Going to over 200 light-years further away, we reach one of my favorite planets on this list, Kepler 186f. This is the outermost planet candidate of a 5-planet system, orbiting for the first time ever a star that isn't a red dwarf. I'm very excited about this. I don't know if I mentioned the type of stars that is prior, but every single planet has to more interesting around the red dwarf. This is what I've seen in space. I'll talk about why it's a planet candidate and not a confirmed planet once I explain its characteristics. Kepler 186f was discovered with the transit method only, with no radial velocity data. Because of this, like Kepler 1649c, it only has a known radius, not a known mass. However, based on its radius, its mass can be constrained, as if it's too large or too small, you need unrealistic compositions. Kepler 186f is definitely larger than 32% of mass of Earth, but definitely smaller than 3.8 times mass of Earth, with an X-median at about 1.44 times mass of Earth, which is coincidentally the exact same hypothetical mass as Proxima b. However, Kepler 186f has a lower equilibrium temperature than Mars. Assuming no atmosphere, its temperature is around minus 121 degrees Fahrenheit or minus 85 Celsius, which is pretty bad for life. However, if it does have an atmosphere, a greenhouse effect could definitely warm it up. It takes about 130 days to orbit the K-type star Kepler 186. This faraway orbit is really good, as for the first time ever, Kepler 186f, if it exists, has about a 50% chance of not being tidally locked to the star, and having an actual day-night cycle. Again, this is a first for this video. The odds aren't great, but they aren't bad either. All in all, things are definitely looking up. Kepler 186 is a calm orange dwarf, and Kepler 186f is very cold, increasing its chances for an atmosphere. Due to this, I think it's very likely that Kepler 186f has an atmosphere, and if that atmosphere is dense and warm enough, its chances of hosting liquid water are high. There's no evidence of this because Kepler 186f has actually only ever been seen once by the Kepler telescope. Nobody's bothered to find it again. This may sound surprising, but this is actually normal for a ton of planets that have the Kepler designation. The Kepler telescope literally just looked at one part of the sky for years on end and found every transiting planet in that space, Kepler 186f being one of them. However, for planets with longer orbits like Kepler 186f, there weren't actually enough transits to confirm it as a real planet. Meaning, technically, Kepler 186f is still a candidate and not actually confirmed to exist. So why does every space website ever list it as confirmed? Well, because up until a few months ago, analysis of the Kepler data showed that the Kepler 186 transits had above a 99% chance of being caused by a planet, that being Kepler 186f. However, recently, a new study came out re-evaluating a lot of this data, and found that Kepler 186f's chances of not existing are much higher than previously thought. It is now expected that there's a 20% chance that this planet isn't real and is a false positive. That still leaves an 80% chance of it existing. However, that's not high enough to list it as a confirmed planet. So Kepler-186f actually used to be confirmed, and then fell back into being a candidate again, which is why most sources still call it confirmed despite the fact that it actually isn't. Anyway, assuming we don't get unlucky and Kepler-186f is real, I think it's almost guaranteed to have an interesting atmosphere. Whether or not it will be a habitable environment is another question, as it could very well just be too cold for life. But no matter what, I don't think this is an airless rock, and if it is real, there is something interesting going on with it. Hopefully someone gets around to looking for it again soon. One important thing I should note for the rest of this video is that almost all Kepler planets suffer from these same problems, including all of the planets I'm about to mention. They were only ever seen a few times by one telescope, and for the most part nobody has tried to see them again. Because of this, there's basically no available information about any of these planets, and no hypothetical models either, because we don't know any of their properties well enough to even begin to model them. So these last few planets will have short entries just to get them out of the way, and then we'll get to the prediction section of this video, where I'll try to guess as to what every planet in this video is like in real life. 620 light years away from Earth, we get to the planet that started it all, Kepler-22b. The first ever transiting planet found in the habitable zone of its star. To make things better, its star is similar to the Sun. This means that Kepler-22b is almost certainly not tidally locked, as it takes 290 days to orbit its star. However, the things that are good about it end there. It's at least 2.1 times the radius of Earth, with yet again an unknown mass. However, its mass is better constrained than Kepler-186f. Unlike most planets in this video, which have minimum masses, Kepler-22b has a maximum mass. It is not bigger than 9.1 times the mass of Earth. This is actually a problem, as any mass lower than 9.1 Earths produces densities that are too low to be a rocky planet. So while we can't say much, Kepler-22b is definitely not a rocky, Earth-like planet. This means that Kepler-22b, if the higher masses are correct, is potentially an ocean planet or a soot planet like I mentioned earlier. If the lower masses are correct, it's a mini-Neptune made of gas with no solid surface. Unfortunately, there's no way of knowing which scenario is more likely right now. We simply know nothing about this planet. It has no neighbors, it has a normal orbit, it's not tidally locked, and it's not rocky. That's pretty much it. It's around a sun-like star, which is nice though. Unfortunately, most of the planets most often talked about by clickbait channels as being likely to be habitable, like Kepler-22b, have almost no actual known information about them. The only reason Kepler-22b is brought up at all in discussions of habitability is because it was the first transiting planet found in the habitable zone. It doesn't actually have anything unique going for it. If this thing was discovered in, say, 2023 rather than 2011, nobody would care about it. The two habitable zone planets of Kepler-62 have many of the same problems. Kepler-62 E and F take 122 and 267 days to orbit their K-type star respectively, but only their radii are known and their masses are largely unconstrained. Kepler-62e is at most 18.7 times the mass of Earth, but the true value is almost certainly far lower because that number gives an unreasonably high density for a planet 61% larger than Earth in radius. Something like 4.5 times the mass of Earth is more realistic. According to a few different papers, it's generally thought that any planet larger than 1.6 to 1.8 is likely to become a gas giant, or anything smaller is likely to be rocky. Kepler-62e is 1.61, meaning it could basically go either way, especially with its unknown mass. This is probably the planet we know the least about in this whole video so far, as there's literally no possible way of telling whether or not it's even rocky, let alone any of its other characteristics. Kepler-62f, however, is only 1.4 times the radius of Earth, making its chances to be rocky a bit higher. Given that it's a cold planet orbiting a larger star, I wouldn't be surprised if it had an atmosphere. But what that atmosphere is anyone's guess. All in all, the Kepler-62 planets, despite being strangely some of the most talked about exoplanets online from what I can tell, literally have no information known about them at all. Hopefully the same is not true about Kepler-442b, 1,196 light years away from Earth. Kepler-442b is yet another planet with a known radius, suggesting it could be rocky, but an unknown mass. It's likely between 8 and 1 Earth masses, with 2.3 times the mass of Earth as a nice middle ground. Its radius is 34% wider than Earth's. A lot of the information about this planet talks about how it's a good candidate for habitability because its star is smaller than the Sun and will thus live longer. This is actually something I've been meaning to talk about on this channel because a lot of people seem to think that K-type stars are the best for life because they're calm and live long. While longer-lived stars may be better for life in the long term, I don't see why K-types would be inherently more habitable than Sun-like stars. The Wikipedia article for Kepler 442b says, for example, it is one of the most promising candidates for potential habitability because its parent star is at least 40% less massive than the Sun, thus it can have a lifespan of about 30 billion years. I don't see how that matters at all. The star isn't 30 billion years old. Kepler 442 is somewhere around 2